The new unit we are starting is dealing with rational expressions. Now, with rational expressions, it's very important that we are able to factor because we're going to be dealing with factors a lot. So we need to be able to factor just generally, but also factor polynomials. So we're going to work on factoring some polynomials today. So factoring is basically rewriting an expression as multiplication of multiplication parts, okay, or the factor parts. So it's very important that we are able to factor when dealing with rational expressions, because when we have a rational expression, we are able to undo a times on the top with a divide on the bottom, and they will cancel out. They will undo each other regardless of whether it's an algebraic expression or a number. They will undo each other and it will equal 1. So it allows us to find equivalent factors. So it allows us to find common denominators, because we're going to need to look at factors when we're finding common denominators, when we're adding, subtracting rational expressions. And allows us to just see basically the component parts. Factored form is often just in general really useful in math. So we can factor these expressions, and the very first thing we always do for any kind of factoring is we look for common factors, or greatest common factors. So we find greatest common factors, we can just check the number parts. 35 and 55 have a greatest common factor of 5. Okay. Then we look at the variable parts, the a and a. I have 23 a's multiplied here, I have 3 a's multiplied here, so the common multiplier is a cubed. We look at the b's. The common b's here, I have 13 here, 1 here, so I have 1b in common, and I have 1c here and 17 c's there, so I have 1c in common. Now, once we factor out the greatest common factor, we also have to figure out what's left. Okay, and we can, since we undid the multiplication, essentially we can just figure out what's left over by division. Okay, so 35 divided by 5. We've taken out 3 a's, so we have 20 a's left. We've taken out 1b, so we have 12 b's left. We've taken out 1c, so we have no c's left there. So 55 divided by 5 is 11. We took out 3 a's here, okay, so there's none left. We took out one of the b's here, so there should be no b's left. And we took out 1c, so there's 16 c's left here. Okay, so there's our factored form. We can check our factoring by just multiplying back together. So at this point we can take a look at this binomial factor, and we can see if we can factor that. That one, there's nothing that we can factor there as a binomial factor, so we're finished for that factoring. So that's the greatest common factor. So I'm just going to make a note here. Always factor the GCF first. Okay. So when we're factoring, we also should think of the area model of factors. So we can show two factors as length times width. So the area model for factoring, so when we have this quadratic factor, we can put this into an area model by showing it as, this is our x squared area. Okay, we have an area of 6 here. And then the 5x area is just going to be the sum of these two areas. So to work that out, we need to split up the 5x. And the way we do that is, well, we can use our our product of 6 here and look at the factors of 6 to find out the edge lengths here and here. So what two factors multiply to 6 and give us the 5x in these two areas? Well, that's going to be 3x and 2x, okay, because we end up with x plus 3 along this factor or side length, and we end up with x plus 2 along this side length, or factor. So that allows us to factor into x plus 3, x plus 2. Okay, so that's our length and width. So that's our area. This is our length times width. Okay, so it's always a good model. Some of you don't need to use that to get the answer here, but it's always a good model to have, because when we start getting into harder problems, we want to have some framework or model that we can use to kind of relate to. So here we'll just practice some of this. So putting this into the area model, okay, we have x squared 42. We need to split up the 13 into these two areas, and those areas are related from this length and this length here. So two numbers that multiply to 42 and add to 13 are 7 and 6. Okay, and then we can find the common side length here is going to be 7. Right? The common side length for these two areas is going to be x, so we have x plus 7. Here we're going to have the common side length here is x, the common side length here is going to be 6, so we have x plus 7 times x plus 6. Okay. So where this model comes in really handy is that when we have this leading coefficient of 2, that makes it factoring a little bit harder, but we set it up the same, 2x squared 5, and we want to be able to split up that 7x. Okay, so now the way we get that split for the 7x, to decompose it into these two areas here, we use a property of the grid multiplication, that this cross product, we get 10x squared, is always equal to the other diagonal cross product. So if you take a look at the one here, it worked here, but we didn't use it. But here we have 42x squared. Along this diagonal, we have 42x squared as well. So we just need to figure out how to split up the area of 7x so that when we multiply them together across that diagonal, we get 10x squared. So the answer in this case would be 5x times 2x. That adds up to 7x, and that multiplies to 10x squared. So once we've done that, we just need to find the common side length, or the common factors here. So this is going to be 2x. The common side length between 5 and 5x, or the greatest common factor, is going to be 5. So one of my factors ends up being 2x plus 5. The other side length, we look horizontally here. The common factor between 2x squared and 5x is just going to be x. And the common factor here is going to be just 1. Okay, so if we multiply this together, we end up with all these 4 area parts. And we end up with our length and width. Or in other words, our factors. Okay, there's our length and width. Now this is a simplified area model. We could use an algebra tile model. Okay, now I think we probably generally want to use the area model, since we can avoid drawing out every tile, but we should be able to do the algebra tiles as well. So if I have 2x squared plus 3x plus 1, I know my 2x squareds have to go together. Okay, and then we know that the 1's going to be in the corner, and we have to be able to arrange the 3x so that we have the 3x tiles around these two, the diagonal parts here. And there's really not much choice. We can draw our x tiles like this, and we need 1 over here. Okay, and so the length of this side is going to be 2x plus 1, and the side length here is going to be x plus 1. So when we factor this, we know this is going to factor to x plus 1, x plus 1. And when we multiply that together, we know that that's going to give us our 2x squareds, our 2x here when we go 2x times 1. Okay, when we do our FOIL, we get our 1x here, x times 1, and then we get our 1 tile here from our 1 times 1 when we multiply out using FOIL.